down again. All right, and it's more modern discussion. Okay. So he came up with Planck's constant. If you look at the units of this, what has the units of a joule second?
It's angular momentum.
Okay, it's not obvious, but later on we'll see the angular momentum. So it turns out that L equals R cross P equals angular momentum, and it has the units of like a length times a mass times a velocity per second. All right, so in SI units, that's meters, kilogram per second times a meter. Meter, kilogram, second, right? And if you multiply that times 1, right, which is 1, a second per second is 1. All right, this comes out to be a meter, kilogram. Sorry, let me write that again. Let me write kilogram, meter, second squared, meter times a second. What's this stuff? That's an energy. Kilogram, this is a meter. That's a joule, right? That's a joule, and that's a second, a joule second. Okay, so what Planck really discovered, and he really didn't take it to the next level, or took it to the next level, is he discovered that L equals, it's a fundamental chunk. So H bar equals a fundamental chunk of angular momentum. Okay, just as, E is a charge of 1 coulomb. 1 coulomb, you're just born with 1 coulomb. All right? Then you're just born with 1 chunk. And you can't have 1.5 chunks of angular momentum. The only way you can have angular momentum is in chunks of 1. Okay? So that was the big deal there. And this is a nice way to remember what H bar is. It's a fundamental chunk of angular momentum. Okay? By the way, I'm probably getting a little bit sloppy here, all right? In that H is Planck's constant. I am getting sloppy. Let me get it correct. H is Planck's constant. Let me get rid of the bar. So let me write it like this. H is Planck's constant equal this number, but it's very convenient. So let me get rid of the H bar there. It's convenient to use H bar, which is just H over 2 pi, which is about 1 times 10 minus 34. So H bar is just H over 2 pi. It's just convenient to use in a lot of places. And here are some numbers. Notice that in these numbers, I'm not getting the number exact. Right? And that's okay, because a lot of times in physics we're just doing order of magnitude calculations. And for all intents and purposes, H is 6 times 10 to the minus 34, or even 10 to the minus 33 if you want. And then H bar is 10 to the minus 34. Okay. Now, Einstein also worked with H bar and showed that light was a quantized wave. Light came in chunks. Alright, where nu equals the frequency in hertz. And again, there's Planck's constant. So what he found out is that in general, for light of a given frequency, you could have n times h bar. So E total, n equals 1, 2, 3, and so on. So that light had this fundamental unit of energy, h times frequency. Right? But the intensity of the light had to do with how many chunks of this that you had. Did you have one chunk of H2? Or did you have 2 chunks of H2, or 3 chunks, or 4 chunks? And then finally, Compton showed that light was like a particle by scattering event. So again, I'm not going to go over the big detail, but what he did is if you treated light like a wave, if you scatter X-rays off of an atom, the light scatters. And if you did the problem with waves, there was all types of problems. But if you treated the light like a particle, and then you use relativistic stuff, relativistic energy, then you get that right.
It's sort of like the slit test that we use in physics class.
The what test?
The slit test where we throw a beam of light through a slit and watch.
That's what I'm getting to. Yeah. All right. So look, this is a big introduction.
You still do the one with the EV and volume?
No.
Oh, really?
Yep. Okay. All of this is modern stuff, so I don't want to get into it much more detail. But look, what's slowly emerging. How many times in emerging?
1.
Okay. Is the idea that light equals a wave plus what's it acting very much like in all these cases, coming in chunks. Alright, that it's kind of acting very particle-like. So in other words, to get everything right, you have to incorporate that light is particle-like as well.
Or you have to show where that particle nature comes from.
Right, ultimately you do, yeah. And ultimately it's waves. Alright?
When you say like Einstein and light, you're talking about visible light. Because Planck wanted to do light. They were working on it.
You can do the photoelectric effect with whatever frequency light you want, visible or not visible.
Right. Planck is, radiation.
Planck is, radiation is visible. I see objects.
Right.
And it has invisible.
Like, so they can be white light, flowing.
It's electromagnetic radiation.
Right.
Okay? So the merging is that light equals a wave plus particle. Alright? Now a couple other things. In 1905, I forgot to mention that we also had special relativity, which is Einstein. Alright, and the big results of Einstein's relativity is essentially that E total equals gamma mc squared. Alright, where that's, again, this is modern physics stuff. Alright, and E total is the sum of the kinetic energy, the potential energy, the inertial energy, the mass. Alright, it's all the energies. And then there's another relationship, E total squared equals, anyone remember this one? So there's a different representation of this. It's C squared, P squared, plus M0 squared, C to the 4. Okay. So these are just reminders. And the reason we're not going to be using it in the Schrodinger equation, all right? I'm going to use it in my derivation later on, so I need it. But I also introduced Compton scattering with the idea right here. The only way you can solve this problem is if you treated light like a particle and use this equation right here. Okay, so again, this is all idea stuff, all right? So look, another thing in physics is that physicists always like symmetry. Right? That symmetry seems to be playing a bigger and bigger role. And, before 1900, we have electrons and particles and lights or waves. That's pretty interesting. And now when you come after 1900, you're getting an idea that light is a wave and a particle, right? So some of the symmetry is gone, right? That, here you have these things. This is a distinct particle, this is a distinct wave. And then this thing is now a particle and a wave. So now light is just a particle and a wave. Might you foreshadow something about an electron?
I think that particles are also wave-like.
Okay, so there might be some experiments that start showing up that light is also, that electrons are also wave-like. Okay? So this is the beginning of the Schrödinger equation. All right, and this is 1912. In 1912, the beginning of and it's the Bohr atom. Okay, so this is very important. So, you got to be able to talk about these things, and hopefully see the story. Okay, so here we go. The Bohr model of the atom. So it's Bohr model of atom. The atom in particular is hydrogen. Okay. So let's start with the Bohr model of hydrogen. Yep, right.
According to the paper you have to read, it's a giant nucleus with the electron floating around it.
The what?
There's a giant nucleus, positively charged and small electrons.
That's right. Yep. So let's treat it with what we know. All right. So there was some positive nucleus, and then there was an electron out here minus. I'll just put that above. All right. And so right now, the physics that you would first try to do, look, this is all new whacked out stuff. That's having to do with light, right? So my first line of attack is going to be some of these, my old theory. So what I'm going to do is this, is I'm going to draw a little cloud around my electron. And so what I'm going to do is assume uniform circular motion. I don't know any better. What I'm going to do is assume that like the moon going around the earth, it's going around in a nice circle. So I'm going to assume uniform circular motion. And when you write down Newton's law for uniform circular motion, sum of the forces centripetal equals minus mv squared over r. Right? That's